We'll be looking at the multiple choice questions for June 2023 paper. Let's make a start. In this question, they ask you which sample contains the greatest number of molecules. Now, when we're dealing with molecules, number of molecules, we're going to have to use Avogadro's number at some point. This refers to number of particles per mole. So really what we need to do is work out the number of moles of each of these hydrocarbons. So we do 35 divided by 26. We've got 45 divided by 30. We've got 60 divided by 58. Yep, 58. And we got 100 divided by 72 and 78. Work out the number of moles of each. Now, as you could see, the one with the greatest number of moles is B. And if you then multiply that by Avogadro's number, it will still be the greatest because it's got the greatest number of moles. So the answer is B. Moving on. You've got an oxide of manganese is reduced by hydrogen gas to form manganese metal and water. It's asking what is the formula of the manganese oxide. Now, you see the oxide is 0.688 grams. And if that's the metal oxide. Now the grams of the mass of water is 0.235 grams. If you divide that by 18, that gives you 0.0130555 moles. Now, you see that's the number of moles of water. Now, the number of moles of oxygen on its own in that water is what we need to work out. So if we get that moles and multiply that by 16, which is the AR of water, of oxygen, that gives us 0.20888 grams. If we deduct that from the mass of the oxide, so 0.88 minus 0.20888, that gives us 0.47912 grams of manganese. This here is the mass of the oxygen. And what we now do, we want to work out the empirical formula of both of them. So we divide both of them by their molar masses to work out the relative number of moles. We've got that already in oxygen, which is here. And manganese would be 0.47912 over Mn. Molar mass is 54.9. Is equal to 0.000 873. And we divide both of them by their smallest number. We've got 1.5. 1.5, which is the ratio of Mn and oxygen. You can't really have a 1.5 and a 1, so we need to multiply that by 2. And that will give you a 2:3 ratio. Moving on. It's asking how many hydrogen atoms are in 2.50 grams of pharmacolate. And what we do again, we work out the number of moles. The molar mass is given in the question over here. And you see per 1 mole of pharmacolate, there are 4 plus 1, which is 5 moles of hydrogen per 1 mole of the compound. So we then multiply that by 5 and then multiply that by Avogadro's number. Two 2.006 times 5 times Avogadro's number, 3.48 times 10 to the 22. And the mark scheme supports that. Moving on. Here, it's asking, you're adding 2 solutions, HCl and NaOH, and you see these react in a 1-to-1 ratio. So what we'll do, we'll work out the moles of each. 0.04 dm cubed multiplied by 0.200 is equal to 0.008 moles. That's the HCl. And this one is 0.06 dm cubed multiplied by 0.100 is equal to 0.006. Now, what you've got here, moles, you see when you react these together, you're going to have an excess, or you're going to have a leftover of HCl, which is going to be 0.002 moles. That is in a solution in 100 centimeters cubed, which is the total. So that gives a concentration of HCl as 0.0200 moles per decimeter cubed of HCl. And so it supports these. Now, because it reacts in a 1-to-1 ratio, 0.006 moles, this is the limiting reagent of NaOH. So that's how much salt is going to be produced, NaCl. So that will be 0.006 moles in 100 centimeters cubed. And that will be this one. So the answer would be C. And the mark scheme supports that. Next question is asking, which compound has polar molecules? You see, before you do this, it helps if you draw these out. H, C, triple bond N. BCl3 will look like this. CO2 is like this. And C2F4 looks like this. If we put in the dipoles, this is going to be delta N is closer to fluorine, so this will be delta negative, delta positive. Delta negative, delta positive. Hydrogen and carbon are usually very similar, so we can maybe disregard the hydrogen for now. Chlorine's delta negative, delta negative, delta negative, delta negative, delta negative, delta positive. Now, which of these compounds is a polar molecule? You see, this one is a symmetrical molecule, so the dipoles cancel out. This is also symmetrical, and the dipoles cancel out. And you see, this one overall is also a symmetrical molecule, and the dipoles also cancel out. But with HCN, this is not symmetrical. Dipoles do not cancel out. Hence, it will be a polar molecule. So the answer is actually A. So these three, call them symmetrical molecules. And the dipoles, the reason for that is the dipoles cancel out. Moving on. Which element has the largest third ionization energy? A question like this, it helps if we just map them out. Lithium is here, sodium is underneath it. Fluorine is in the same period as lithium. Neon is next to fluorine. Yeah, that's four of them. You see, we want the largest third ionization energy. It's not going to be neon or fluorine because their third electron is still removed from the same outer shell. It's not going to be sodium because as you go down, the ionization energy decreases. So it's going to be lithium because the third ionization energy, you're actually removing from the inner shell. Lithium has only got 3 electrons as well. 1, 2, and then 3. It's the smallest. It's going to have the least amount of shielding. And it's going to have and these factors gives it the greatest third ionization. 1, first electron removed, second electron removed, third electron removed. Even though these two have a greater number of protons or nuclear charge, but they're being removed from the outer electron shell, this electron shell, whereas lithium, you're removing the third electron from the innermost shell. So the answer will be A. And the mark scheme supports that. This is an A2 question. It's asking, the reaction below is first order with respect to reactant X. When the initial concentration of X is 1 mole per decimeter cubed, it's got this half-life. What is the half-life when the initial concentration is doubled? It makes no difference. If it's a first order, the half-life always remains constant. And so the half-life will still be 16 minutes. And the mark scheme supports that. Which compound requires the most energy to convert 1 mole into its gaseous ions? Now, you see, this is kind of indirectly linked with lattice entropy. Lattice entropy is when you've got your gaseous ions forming the ionic compound, but we're looking at the reverse. You see here, really, we've got sodium ion versus the magnesium ion. And we've got the fluoride ion versus the oxide ion. Which energy requires the most energy? Which compound requires the most energy? You see, the Mg2 plus ion has a greater ionic charge. Greater ionic charge versus sodium. And again, the oxide ion, greater ionic charge, and it's also smaller ionic radius versus sodium. Remember that how the ions, the size decreases across the period. Smaller ionic radius. And for the oxide ion, you've got a greater ionic charge. And you see these factors, greater ionic charge, even though it's going to be slightly bigger than the fluorine, but the fact that the ionic charge is double that of fluorine, that's the greater factor here. And you see these, all in all, these create a greater charge density. These two factors of size and charge. Both of these have a greater charge density. And so this will require the most energy to convert them into gaseous ions. There'll be the greatest attraction between. Entropy. So what we've got here, what is the standard entropy change for the formation of SO3? Oh, this is a liquid. For the formation of SO3L, so it'd be a gas. Liquid from SO2 and O2. These are gases and these are gases. And to balance, you've got a 2 there and a 2 there. So you've got 3 moles of gas gives you 2 moles of a liquid. You are actually losing disorder. You're losing it, so it's going to be a negative entropy change. If you're losing disorder, you get 3 moles of gas to give you 2 moles of a liquid. It's going to be one of those two. Now let's do the calculation. So the calculation for the entropy change will equal, it's always the products minus the reactants. So the products is going to be 2 times 96 minus 248 times 2, and we've got an oxygen. I've got minus 508. And the mark scheme doesn't support that. What's going on here? Products minus reactants. What have we done wrong here? Minus 508. The answer is saying B. Ah, I didn't read it properly. For the formation of 1 mole of SO3. This is the formation of 2 moles of SO3. So we want to halve that value. So we do that, and then we divide by 2. And then it will give you minus 254. So this is crossed out. B. Read the question carefully. Moving on. This is what is the percentage dissociation of this weak acid. Now, to work out the percentage dissociation, we need to work out the concentration of the H plus ions. We got the values. We're going to multiply this by the concentration, and we then take a square root to work out the concentration of H plus ions. And you see, to work out the percentage, it's going to be this answer divided by, that's the concentration of the H plus ions divided by the concentration of the weak acid. .32. Answer is D. And the mark scheme supports that. Potassium carbonate, A2CO3, to 1 test tube, and aqueous silver nitrate to a 2nd test tube. The student adds dilute hydrochloric acid. Hydrochloric acid will react with the carbonate to give you bubbles. So it's going to be either one of these two. And when you add it to silver nitrate, you see you got H plus ions and chloride ions. The silver nitrate will react with the chloride ions to give you a precipitate, a silver chloride precipitate. And so the answer would actually be D. Moving on. We've got a question on electrode potentials. You got 2 electrode potentials here for a lithium ion cell. You've got the 2 half cells. And you see which is the correct statement. So we'll go through each of these possible answers. The cell potential is 2.88 V. So it's always the positive minus the negative. And the answer is actually 4.20 volts. So this is wrong. The reaction at the positive electrode is this. So can you see what's happened here? This is this equation, but flipped. And it would not flip because this is the more positive of the 2 electrodes. The electrode potential is more positive. So this would not happen. This reaction would not happen. The overall cell reaction is LiCO02 which is these two, and goes on to give you wait a minute, what's going on here? Yeah, it's not this one. So it's going to be, this gets flipped around because it's the more negative one. Let's flip this over. So this will be Li plus Li to go on to give you Li plus an electron. And what will happen? What's on both sides gets cancelled out. And you've got, yep, this is actually correct. This is actually correct. The oxidation number of CO changes from +2 to +1. No, it doesn't. CO02 goes to LiCO02. So it goes from a +4 oxidation number to a +3. So this is actually wrong. So the answer is going to be C. Yep, mark scheme supports that. Next question. Which substances have induced dipole-dipole interactions, London forces, in the solid state? So what you've got here, you've got ethane. You've got, in the solid state, you've got ice. And you've got silicon dioxide, which has a giant covalent structure. Now, 3 is going to be ruled out because that's held together by strong covalent bonds. Ice is held by London forces, but the main intermolecular force is hydrogen bonding, but it does have London forces in it. And ethane, in its solid state, when it's frozen, will also have London forces. So the answer will be 1 and 2. Yep, the answer is B, supported by the mark scheme. Just a reminder, students will think ice only has hydrogen bonding. It will have hydrogen bonding and London forces, but we talk about the hydrogen bonding because they are more significant. They are more significant, I believe, by a factor of, I've done these, something like a factor of, it's either 40 plus, 40 plus or 20 plus. Anyway, 20 times. We're nearly near the end. So here, which statements are correct for anti-cancer complex? You got a complex here. Now this complex, if we draw it, these are behind the page or behind the board. So there's different orders these can take place. Let's put the ammonias at the back. And then you've got the bold bonds of the chloride. It's a square planar complex. Bond angles are 90 degrees. Yes, they are. It's a square planar. The oxidation number of platinum is +4. Let's check that. Chloride ion is -1, -1. Ammonia is 0, 0. Platinum must be +2. So no, it's not going to be 2. And the third one, it forms both optical and cis-trans isomers. It can form cis-trans isomers. If you flip these over, it will give you cis-trans. However, it's not an optical isomer. Optical isomer is where the the mirror image is non-superimposable. And the mirror image of this would be imposable. So it would not be number 3. So the answer is only number 1, which is D. And the mark scheme supports that. Last question. If you look at this question here, you've got a green gas here, a yellow gas here, and a colorless gas here. You've got equilibrium setup, which is this a redox reaction? Let's check. Oxidation number is 0, 0. Chlorides are -1, -1, -1. That's +3. This is a redox reaction. When the equilibrium mixture is cooled, the color fades. When it's cooled, you've lowered the temperature to oppose that change in equilibrium with the exothermic direction. So it will go from, so the equilibrium will shift to the, so how you're cooling it. You want to bring the temperature back up. Yeah, exothermic, it'll turn to the left-hand side, which is the color fades because it gives you a colorless gas. 2 is correct. The decomposition has a negative entropy. You are getting 4 moles of gas and turning it into, sorry, the decomposition. Decomposition is 2 moles of gas to give you 4 moles of gas. The entropy, you are gaining entropy, so the entropy should be positive for the entropy change. So number 3 is not. Answer will be B. And the mark scheme, ladies and gentlemen, supports that. That's the end of the multiple choice questions. I'll see you next time.